Alright, in this video we're going to be looking at the rules of anti-differentiation, which we write using indefinite integrals. So we're going to call this our elementary integration rules. Now every rule of differentiation we should be able to think of as a corresponding rule for anti-differentiation. So let's look at some of these. First, we know how to differentiate a power of x. So if I take a derivative of x to power n plus 1, I'll multiply by the power times x to the n. The idea of integrals is that this is the antiderivative. Sorry, this is the derivative. And what's inside what we differentiated, that's the antiderivative. So if I wrote this as an integral, it would say if I took the integral of n plus 1 times x to the n dx, I'll get the antiderivative, x to the n plus 1 plus a constant. Now, we usually think of this, we don't want to have this n plus 1 normally. So if I think about dividing both sides of my original formula by n plus 1, I can get my ordinary rule of integration. If I integrate x to the n dx, I'll get 1 over the power n plus 1 x is raised to the power n plus 1, and every time we do an indefinite integral we're going to have to remember to add the integration constant. So let's look at a couple other rules of derivatives. If I take a derivative of the logarithm of x, I get 1 over x. And if I include absolute values, I get both positive and negative x. So what do we have? We have this is the derivative. That's what will go inside of the integral. And this is the antiderivative, or the one of them, because we have infinitely many. So our rule of integration says if I integrate the derivative, we should get back to the original function, which in this case is the natural log of the absolute value of x plus a constant. Okay. And our third example, we know how to differentiate e to a power of constant times x. I get e to the kx times the derivative of kx, which is k. And again, if I were to write this as an integral, the integral of the derivative dx will recover the original function e to the kx plus our constant. And we normally want our rule not to include the constant k, so if I wrote the integral of e to the kx, well, what would it take? I would need to I would need to divide both sides here by k. So I get the original function is now 1 over k e to the kx plus c. So these are the three basic rules we're going to be using as an integral of 2 times x to the negative 3 power dx. So now I've got a power n equals negative 3. And I can use my power rule I've got a constant 2. What would be the power n plus 1? So if I add 1 to that, I get negative 2. My derivative, I'm going to be 1 over the new power times x to the new power. That's what the rule predicts. And then we should have plus a constant. So if I simplify that, 2 over negative 2 is negative 1. X to the negative 2 becomes in the denominator. And here is my proposed general antiderivative. Now how would we check? We check derivatives by using, we check antiderivatives by using the differentiation operator. So what would I get if I took a derivative of negative x to the negative 2? The constant doesn't matter. The differentiation of a constant is 0. So let's see, I get negative 1 times negative 2x to the negative 3. And the negative signs cancel. And so I'm left with 2 over x cubed. And that matches my original formula, the integrand inside of the integral. So we have the right derivative. Okay, let's do the next one. So our second problem, we have the integral of 4 over x. The derivative is supposed to be 4 over x. So how can we get that? Well, the 4 is a constant, so we could think of that as being, we need 4 times the integral of 1 over x dx, which we should remember is the derivative of the logarithm. So it's 4 times the logarithm of the absolute value of x, so that we get our domain positive and negative, plus c. This is the integral. We've got a antiderivative for natural log absolute value of x plus a constant. And we check, of course, by seeing if we get the right derivative. So 4 natural log of the absolute value of x. 4 is a constant multiple. Derivative of natural log of x is 1 over x. And we get, again, the same formula as is in the integrand. This is what it means to be an antiderivative. We found a function. We found a function that has a derivative that's 4 over x. Alright, so let's look at our last example here. We've got the integral of e to the 3x. So we need to remember the integral of an exponential is an exponential, except that we would get this if we did a derivative of e to the 3x. We get e to the 3x times the derivative of 3x, which is 3, and this function doesn't have the 3. And we can fix that by getting 1/3. So we should have 1/3 e to the 3x plus c. This is our claim. And we could check that. Let's see if I took a derivative of 1/3 e to the 3x. Now the 1/3 is a constant. And then we already know the derivative of e to the 3x is 3 e to the 3x. The 3's and the 1/3 cancel, and I get e to the 3x, which is what we needed.